Wahlberger, and welcome to the Algebraic Calculus 2 course. We're going to talk about the Chu Vandermonde identity today in the context of trying to establish this very important relationship that we call Newton's Polyseries theorem, which is a sort of foundation for the modern theory of power series, or we'll prefer to say Polyseries. Okay, so let's start off with the reminder of the two different ways we have of thinking about binomial coefficients. So n choose k, okay? Combinatorially, if n is an integer and k is an integer, positive integers, then this is counting the number of ways of choosing k things from n. And the formula for it is this one here. That's one formula. Sometimes it's expressed as n factorial divided by k factorial times n minus k factorial, but you can do some cancellation and write it like this. So it's n times n minus 1 all the way to n minus k plus 1 all over k factorial. And this numerator here is conveniently expressed using Knuth's falling power notation. So we write it as n to the k falling, with a little bar underneath the k. Okay? That means that there's going to be k products involved here, okay? And but they're not all equal to n. They're going down by 1 each step. So n times n minus 1 times n minus 2 down to n minus k plus 1. And altogether there are k such products. Now, this number here, we can think of it as being an element in the Pascal matrix, or the Pascal-Harriot array, as we prefer to call it these days. And traditionally, we can think about the entries here as we fix n and move k along, that what we're doing is we're going across the rows, okay? And so the familiar like 1, 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, etc. But there's another way of thinking about this same array where we're going down the columns. So we think of it as a function of n that depends on k. Okay? It's just two different ways of thinking about it because there's two variables floating around here. Now, there's an advantage in thinking about this one because as a function of n, this is a polynomial in n. Okay, if you fix k, this is a polynomial in n. And in particular, it therefore has an obvious extension to non-natural number values of n. It's a polynomial, so you can evaluate it at negative numbers, you can evaluate it at rational numbers which are not necessarily natural numbers. And this corresponds to what we call the Harriot basis. These are the columns of this Harriot array. So each h sub k is a polynomial function, so it extends to h sub k of r for r a rational number. And it's that usage here that allows us then to bring into being Newton's binomial series, okay, which is a generalization of the usual binomial theorem for 1 plus alpha to the n to define out of thin air 1 plus alpha to the r, where r is a rational number, possibly negative. Okay, and here is the definition. It's a Polyseries. It's like a polynomial in alpha, but it keeps on going, okay? Where the coefficient of alpha to the k is running from 0 onwards up, so k equals 0, 1, 2, 3, 4, etc. And I indicate the fact that it's carrying on with this plus sign here. So I'm not saying that we're going to go to infinity, because that would involve an infinite number of steps, and we do not believe in pretending that we can do that, right? Good. So we're just going to use this notation instead. It's more modest. We see this thing as going off into the distance as k gets larger. And what is the coefficient of alpha to the k? It's exactly this quantity here, h sub k, but now of r. So we're just taking this thing here and replacing n with r, which is valid since r is a rational number. And explicitly, in terms of a series, so you can kind of see what the initial terms are, is 1 plus r alpha plus r times r minus 1 over 2 factorial alpha squared. So this is like h2. And then the next one would be r times r minus 1 times r minus 2 all over 3 factorial times alpha cubed, etc. So this is some kind of ongoing polynomial ongoing polynumber, and we do not have a complete theory of such things yet. So I'm putting this in quotes here, okay? And one of our aims is to try to really understand what's going on here. But there are, let's say, a number of different possible points of view that we could have to such a thing. And at this stage, we want to be a little bit agnostic and open-minded about, which ways ultimately we're going to try to clarify things. In any case, what we want to do is to establish or convince ourselves of this fundamental relation. It's this relation that puts this story on the map. That if we have two rational numbers r and s, and we take this series 1 plus alpha to the r, notice the pointy bracket on the right, times 1 plus alpha pointy bracket to the s, that equals 1 plus alpha pointy bracket to the r plus s. Now, first of all, how should we interpret this? Okay, we have here are two of these Polyseries. They keep on going. They're the polynomials in alpha, if we read it out like this, but they just keep on going. We're proposing to multiply them together and to compare the result with another one, something like that, where now the r is replaced with r plus s. So what is the meaning? Well, the meaning is not in terms of functional evaluation. Okay, so you may be used to, from traditional calculus courses, the idea that we're thinking about this as a power series and that represents a function from real numbers to real numbers. Okay, so absolutely not. Okay, wipe that idea completely from your minds. That's not what's happening here. We are adopting rather a more combinatorialist point of view, where we think of these things as sort of formal objects, just the way we think of polynumbers as not being functions, but just as being formal expressions of a certain kind. So what is the meaning here? Well, the meaning is the natural one, that if we look at any power of alpha on the right-hand side, okay, so this is a Polyseries, so we look at some power, say alpha to the 10, then we ask, okay, what's the corresponding power on this side? Well, over here, when we multiply these two Polyseries, the terms that are involved with alpha to the 10, say, will be finite in number. We'll only have to go up to the 10th term in each of these initial sequences in order to calculate the alpha to the 10 coefficient in the product. Okay, that's the way Polyseries multiplication works. So crucially, the coefficient of alpha to the 10 on this side is a finite number that we can compute. And so the claim here is that that coefficient of alpha to the 10 is equal to the coefficient of alpha to the 10 on this side. And that's true not just for 10, but also for 11, in fact, for any natural number. Okay, so that's the meaning. That's what we want to head towards understanding. And this Chu Vandermonde identity is a core ingredient in this understanding. All right, so let's have a look at this identity that we're trying to establish. Here is 1 plus alpha to the r, that Polyseries that we're thinking about. Summation over k of h sub k of r alpha to the k. R is some rational number. And the summation is k equals 0, 1, 2, 3, and so on. And over here, a corresponding sum, powers of alpha, say L equals 0 and onwards, h sub L of s alpha to the L. So s is the other rational number. And here is the right-hand side, a similar kind of thing, let's say summing over m, h sub m of r plus s alpha to the m. So let's write out these sums a little bit more sort of explicitly. So the first one is 1 plus r alpha plus r minus 1 over 2 factorial alpha squared, and so on, higher powers of alpha. And over here, corresponding thing for it with s's, and over here, corresponding thing with r plus s instead. All right? So it's this identity that we want to establish, even though the whole thing really should have quotes around it, because we haven't exactly understood what we mean by these three dots yet. But nevertheless, we can clarify what it is that we want to prove. We want to show that for any power of alpha, if we calculate the coefficient of that power of alpha on the right side, and on the left side they agree. So let's have a look at the special case where we're looking at alpha squared. What about the earlier powers? Well, the constant term here is 1 and the constant term here is 1. They obviously agree. So the linear terms, well, there's an r alpha times 1 and there's a 1 times s alpha, so that's r plus s times alpha. That's the same thing as happening over here. So what about the quadratic terms, the first place where it's kind of interesting? On the left-hand side up here, the quadratic terms, well, there's an r times r minus 1 over 2 factorial times an alpha squared times that 1. So that'll give us that coefficient there. And then this alpha times that alpha will give us a factor rs. And then this times this will give us an s times s minus 1 over 2 factorial. So this is the coefficient of alpha squared on the left-hand side. And the coefficient of alpha squared on the right-hand side is just this quantity here, r plus s times r plus s minus 1 over 2 factorial. So this is then an identity that we want to prove. We want to prove this identity for rational numbers r and s. And it turns out that this is a special case of the Chu Vandermonde formula. Now Chu, interesting Chinese mathematician. Sometimes his name is also spelled Zhu, Z-H-U. His first name is something like Shi Jie. He lived in around 1300 in China and traveled around and wrote and has quite an interesting story. He actually discovered quite a few things that European mathematicians later got credited for. Things like Pascal's triangle and so on. So rather important things, including this formula here that we're talking about. And then considerably later, more than 400 years later, Vandermonde, who was an 18th century European mathematician, discovered essentially the same formula, of course, independently. Okay, so this is a special case. So our first order of business is to check, is this a true statement? Well, the first thing we might like to do is to clear the denominator of that 2 factorial that appears in some of the terms. So if we multiply by 2, then we get r times r minus 1 plus 2rs plus s times s minus 1 equals r plus s times r plus s minus 1. Now, it's easy enough to expand both sides and see that they're the same. But actually, I want to point out a way of thinking about this, which is oriented towards establishing this result inductively. So right now we're just looking at the quadratic terms, but ultimately we want the cubic terms and then the quartic ones. In fact, we want the general coefficient of alpha to the end. And so to establish corresponding identities, it turns out these things are a little bit non-trivial, and we're going to proceed inductively. So I want to illustrate the crucial inductiveness right here at this example. So let's start with the earlier identity that we already have observed, that the coefficient of alpha on one side is r plus s, and that's equal to the coefficient of alpha on the other side, r plus s. So let's take this thing here, which is essentially the degree 1 form of it, and multiply both sides by r plus s minus 1 with a view of getting this right-hand side. Okay, so now what we're going to think about is, let's look at this product here on the left-hand side. I want to use the distributive law. So I want to write this as r times this plus s times this. That's what I'm doing here. So this is r times this plus s times this. But I'm rewriting this term r plus s minus 1 crucially in a subtly different way in these two cases. So over here, I'm writing this as r minus 1 plus s, and thinking of the r minus 1 as sort of one object and the s as the other one. And over here, I'm rewriting it as r plus s minus 1. Now, this makes it easier to see that when we expand this out, we're going to get actually the left-hand side here. Because the r times r minus 1 that we've cooked up here is exactly this first term. And the s times the s minus 1 that we've cooked up here is the last term. And this 2rs is coming about as a sum of two different contributions. One of them is the rs that's coming from this product, and the other one is the sr, which is coming from this product. So this is a little trick, okay? It's a little trick of rewriting r plus s minus 1 in various ways, in these two different ways, And this turns out to be the key to an inductive proof. And later on, we'll see an important generalization of this entire story that essentially still rests on this same trick. So please make sure that you fully appreciate what I've done here, even though it's very elementary. All right, so now let's look at the coefficient of alpha cubed on both sides of our Newton Polyseries theorem. So to do that, we're going to have to sort of expand the view of our polyseries, go a little bit further, exhibit more of it. So we're going to exhibit the 1 plus alpha to the r, now up to things of degree 3 in alpha. And here is 1 plus alpha to the s, also up to degree 3 in alpha. And the right-hand side, which is 1 plus alpha to the r plus s, will also expand that out up to terms alpha cubed. So what's our job now? Our job is to figure out why the coefficient of alpha cubed on both sides is the same. The coefficient of alpha cubed on the right-hand side is just this term here. That's immediate. And up here, how can we get a term alpha cubed? Well, one way is to take the 1 here times this term here, which will give us this r times r minus 1 times r minus 2 over 3 factorial. Okay, so that product there is the first constituent. And then the next one is, say, this s alpha times this term here, in which case we get r times r minus 1 over 2 factorial coming from there times s. Okay, so we multiply those two. And now we multiply this alpha squared with that alpha, giving us r times s minus 1 over 2 factorial. And finally, this times the 1 here gives us the s times s minus 1 times s minus 2 over 3 factorial. So this is then the corresponding Chu Vandermonde identity that we need to convince ourselves of in order to establish that these two sides agree up to degree 3 in alpha. So it's getting a little bit more complicated, but it's a very interesting identity. So why is this thing true? Well, suppose for a second that r and s are not general rational numbers, but they are natural numbers for a second. Okay, they're natural numbers. In that case, these numbers that are appearing as coefficients of alpha in these polyseries have this combinatorial interpretation as, n choose k. So the alpha squared identity that we've just been talking about can be expressed as r choose 2 plus r choose 1 times s choose 1 plus s choose 2 equals r plus s choose 2. That's just a way of rewriting what I have originally written, but now using the binomial coefficient notation, which usually assumes that r and s, these numerators up here, are actually natural numbers. And correspondingly, the identity we've just been looking at, the coefficient of alpha cubed, that can also be expressed in terms of binomial coefficients as r choose 3 plus r choose 2 times s choose 1 plus r choose 1 times s choose 2 plus s choose 3 equals r plus s choose 3. So this is another form, another way of writing these Chu Vandermonde identities in the cases of degree 2 and 3. Now, when we think about it this way, in terms of number of ways of choosing something from something else, we are talking about a combinatorial interpretation, and we can understand what this equation means, or any of these equations, in terms of combinatorics. So in the for the alpha cubed case, both sides of this equation here are counting the number of ways of choosing 3 things from r plus s things. Okay, so you've got a bunch of things, and there's r plus s of these things, okay, represented by this big box here, and there's r of a certain kind and s of some other kind. And we're interested in choosing 3 things from the entire collection. Now, the number of ways of doing that is r plus s choose 3, what's appearing here on the right-hand side. What the left-hand side is doing is counting this in a more refined manner by separating the different cases of how many of our objects are going to be appearing in each of these boxes. So this box here is the case when we are taking our 3 objects all from the r things. Okay, there's r choose 3 ways of doing that. So here's the case where we're taking 2 from the r and 1 from the s. So the number of ways of doing it this way is r choose 2 times s choose 1. The number of ways of doing this is r choose 1 times s choose 2, and the number of ways of doing this is just s choose 3. So this combinatorial interpretation makes the truth of the identity almost immediate, okay? Which is why Chu was able to discover this. It's a very natural relationship when talking about elementary combinatorics, in fact. But for us, we have an additional challenge in that we're not really finished because we're trying to establish this identity in the more general case when r and s are rational numbers, maybe even negative numbers, where the meaning of such a combinatorial expression is much more ambiguous. Okay, so let's go back to our degree 3 identity and go back to the situation where r and s are now rational numbers. And just as in the quadratic case, let's clear the fraction. So we're going to multiply by 3 factorial to clear the denominators. And then the required identity is r times r minus 1 times r minus 2 plus 3r r minus 1s, because there's a 3 factorial over a 2 factorial, plus 3rs times s minus 1 plus s times s minus 1 times s minus 2 equals the product r plus s minus 1, r plus s minus 2. So again, we could just expand things out and observe that the left-hand side equals the right-hand side. But we want to be a little bit more clever because we want to understand this inductive step that allows us to go from one value to the next degree. So the inductive proof step. Multiply the degree 2 identity, the one that we've already established, by r plus s minus 2 and rearrange. So now if you understand what I'm doing right here, then you will understand a broad algebraic proof of this Chu Vandermonde identity. And I think this proof is, well, it's a novel to me, but very likely somebody will have discovered this already. But anyway, I think it's interesting because it crucially is quite general. It doesn't really depend on the nature of r and s. So here is the identity that we've already established in the degree 2 case. Okay? We're comparing this with this. What we're going to do is we're going to multiply by r plus s minus 2. So that's obviously going to take this right-hand side to the required right-hand side. So then the problem will be, why is it that when we take this expression here and multiply by r plus s minus 2, that we get something that can be arranged like this? Okay, so let's do that. We'll do it term by term. Okay, so we're going to take this r times r minus 1 and multiply it by r plus s minus 2. But I'm going to write that r plus s minus 2 as r minus 2 plus s. Fine. Now to the next term, 2rs. And I'm going to multiply it by r plus s minus 2. But I'm going to write that r plus s minus 2 this time as r minus 1 plus s minus 1. And finally, s times s minus 1. I'm going to still multiply by r plus s minus 2. But I'm going to write it as r plus s minus 2. And now let's stare at this, and we'll see that when we expand this out, we get r times r minus 1 times r minus 2. That's exactly this term on this side here. And this s times s minus 1 times s minus 2 is obtained from here times here times here. The terms that we haven't yet taken care of are the r times r minus 1 times s. Okay, so there's one of those. But over here, this product, this term times this first one is also an r times r minus 1 times s. And there are two of them. So we're picking up this thing here because one of them is coming from this factor and two of them are coming from this factor. Similarly, this 3rs s minus 1, 1r and 2s terms. So if we take this r and look at the s times the s minus 1, that's going to give two of these three things. And the other one is coming from here, s times s minus 1 times r. So a total of three of them. So altogether, all these pieces kind of slot together and they match up, and we're able to deduce the cubic identity from the quadratic one. And if you've observed this carefully, you can see this is a kind of a nice pattern. It's starting to be predictable. You can kind of guess what's going to happen if we go from alpha cubed to alpha to the 4. And I suggest that you write that out. And once you've written that out, you'll see that you're basically in possession of a general inductive proof that will work to get you from alpha to the n to alpha to the n plus 1, even though it might be a little bit more cumbersome to write it out. In the actual online course, of course, we're going to go through all of that, make it all cut and dried, but it's a good exercise for you to try to write that down yourself. All right, so let's summarize what we've done and generalize it just a little bit. Okay, so we'll call this the Chu Vandermonde polynumber identity. We're going to shift gears just a little bit again, and after having done those manipulations, we can start to appreciate that, the fact that R and S were rational numbers, we didn't really use that. Okay, in fact, we could have framed the argument where R and S were rather variables. Well, in our world of algebraic calculus, we prefer not to talk about variables, except informally. But we have polynumbers that do the same job. Namely, alpha and beta are two basic bipoly numbers, right? So what we can do is we can replace R and S with basically alpha and beta, thereby giving a pure polynumber form to the Chu Vandermonde identities. And they, of course, exist in each degree, and so let's just have a look at the first few degrees. So degree 0, let's include it as well. 1 equals 1. Degree 1, alpha plus beta equals alpha plus beta. Okay. Degree 2, here is that expression, but now instead of having R's and S's, we just have an expression in terms of bipoly numbers. Alpha minus 1 plus 2 alpha beta plus beta times beta minus 1 is alpha plus beta times alpha plus beta minus 1. And the degree 3 term, well, it's the same story, just exactly what we've been looking at with R's and S's replaced with alpha and beta. And now we can pretty easily see what the general form is going to be. So if we're in degree n, then the first term here is alpha to the n falling. Like this is alpha to the 3 falling. And then we have a bunch of terms whose coefficients are just following the Pascal triangle, the binomial coefficients corresponding to n. So we have n choose 1, n choose 2, n choose 3, all the way up to n choose n, which is 1. And the terms here, well, the falling power of alpha gets lower. So instead of having alpha to the falling 3, now we have alpha to the falling 2. Okay? And then there's the beta that appears. And then the next term, the alpha to the n minus 1 falling decreases to alpha to the n minus 2 falling, while the beta falling power increases. So it becomes 2 falling. So the alpha falling powers are decreasing, the beta falling powers are increasing, until finally we just have beta to the n falling. And on the right-hand side, well, it's just alpha plus beta to the n falling. So now we've sort of removed the combinatorial aspect. Now it's pure algebra. In fact, expressed just in terms of the polynumber language. Now you probably noticed that Chu Vandermonde identity is very similar to the binomial theorem. It's sort of remarkably analogous. And let's write that down and just to clarify that in our minds, because it's a very interesting and important point. So first of all, maybe we should start with the binomial theorem. Okay? If you just have alpha plus beta to the n in the world of polynumbers, and you expand that out, you're going to get the sum from k equals 0 to n choose k, alpha to the n minus k, beta to the k. Increasing powers of beta, decreasing powers of alpha with binomial coefficients as coefficients. Now, our Chu Vandermonde identity, which we've just established, okay, or at least I've given you the outline of an inductive proof for it, can be written this way. This is just a rewrite of what I've wrote out more longhand. This is alpha plus beta to the n falling equals summation k equals 0 to n choose k, alpha to the n minus k falling times beta to the k falling. There's something amazing about this, that this fundamental theorem that all students of mathematics learn and appreciate has an almost direct verbatim analog where you replace the powers with falling powers Just replace each of these powers with falling powers, and that's all you do to go from this one to this one. That's all. So for example, if there was a beta to the 5 over here at some point, over here there'd be a beta to the 5 falling. So you'd have to replace the beta to the 5th with beta times beta minus 1 times beta minus 2 times beta minus 3 times beta minus 4. And it's still an identity. Now, once you've seen that so clearly, your natural mathematical, curiosity will maybe suggest to you, okay, but what about rising powers? What's going on there? Here's the rising power notation due to Donald Knuth. Okay, so alpha to the n rising is, well, again, it's a product of n things, but now we're increasing the thing that we're multiplying by 1 each time. Alpha times alpha plus 1 times alpha plus 2 all the way up to alpha plus n minus 1. Altogether n terms. So the corresponding thing, well, just replace the falling things with rising things. Alpha plus beta to the n rising equals summation k equals 0 to n choose k. Alpha to the n minus k rising, beta to the k rising. Is that still true? Well, it turns out that it is. It's still true. We could call this the rising Chu Vandermonde identity. It doesn't appear to be quite as well known as this one here, but there's obviously a symmetrical aspect, and this one, on the face of it, looks just as good as that one. In fact, once we see these three beautiful formulas like this, we're naturally compelled to ask, okay, is there some sort of unified? Can we put all of these together in one package? In my next video, I'm going to show you that we can do just that, and that it has interesting consequences. I hope you'll join me for that. I'm Norman Wahlberger. Thanks for listening.